Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 12. In this lecture, we'll discuss sound waves. This topic is covered in Chapter 17 of our textbook by Surway and Jouet. Let's begin with a verbal definition of what a sound wave is. A sound wave is the periodic longitudinal displacement of atoms or molecules from their equilibrium positions in an elastic material medium. So a sound wave is a periodic phenomenon. It repeats itself, much like the other wave phenomenon, like rope waves that we've been studying. As you will eventually see, the mathematics of sound waves is very similar to the mathematics of rope waves. You also need to recall what the polarization of a wave means. Remember that there are two polarizations, longitudinal and transverse polarization. Rope waves have transverse polarization. Sound waves, on the other hand, have longitudinal polarization. And sound waves can propagate through any elastic material medium. We often speak of sound waves as traveling through air, but in general, sound waves can travel through any material medium in which the atoms or molecules are free to oscillate relative to an equilibrium position. To better understand this definition, it helps to have a picture or an animation in mind. So this is what sound waves inside a column of air might look like. Imagine, for example, the column of a musical instrument like a flute or an oboe. Imagine that sound waves are being generated on the left end through the vibration of, let's say, a reed, or this could be, for example, your vocal cord as you speak. And as a result of the vibrations of the source on the left side in this picture, air molecules begin to move. As you can see, the motion of the air molecules is periodic. You can track the motion of any one molecule. For example, this red molecule here, and you can see that it's basically oscillating left and right relative to some equilibrium position. This red molecule here is doing the same thing. Of course, as you can see, energy is propagating from left to right. So as usual, there is a wave velocity that indicates the motion of energy. And then there is also the element velocity. That's the velocity of individual molecules or atoms of the air. And those two velocities are parallel to one another. Hence, we say that sound waves have longitudinal polarization, or that the displacement is longitudinal, as in along the length of the column of air in this particular case. I'm speaking of sound waves in air here, but a similar picture would apply to sound waves propagating, for example, in water. The thing that would be moving, the thing that would be oscillating relative to an equilibrium position, in that case would be water molecules. Let's mention some important properties of sound waves. First of all, sound waves are three-dimensional waves. This means that the energy of the wave can propagate in all three directions of space. Here I'm not talking about the dimensions of a graph that you might choose to draw of the sound waves. Here I'm specifically talking about energy and the number of directions or dimensions in which it can propagate. If you generate some sound waves by, for example, clapping your hands, the energy of those sound waves can propagate in the x direction, the y direction, or the z direction. Hence, we say that sound waves in general are three-dimensional. On the previous slide, I showed you an animation in which it looked like the energy was propagating in only one direction, but a little more generally, you can imagine the energy propagating in two or three directions. For example, in this animation, what we have is a speaker, something like an audio speaker, the kind of thing that you're probably using to hear these lectures right now. And this audio speaker consists of a diaphragm that vibrates. And as it vibrates, it displaces air molecules near it. And those air molecules communicate with other nearby air molecules. And so the disturbance, the energy, propagates outwards. In this case, you can clearly see that the energy is propagating along the x direction, both positive x and negative x. It's also propagating in the y direction, both positive y and negative y. And with a little bit of imagination, you can imagine that these sound waves could also propagate in the z direction. Hence, we say that in general, sound waves can be three-dimensional. Sound waves are longitudinal waves. Their polarization is longitudinal. What that means is that the element velocity, the velocity of individual molecules of air, for example, and the wave velocity are parallel. If you focus, for example, on one of the molecules here, you can see that the molecules there are moving left and right, let's call that the x direction, and the wave energy also propagating to the right along the x-axis. Now you can go up here and focus on the molecules there. Above the speaker, the molecules are moving in the y direction, and the wave is propagating in the y direction as well. So we would say that everywhere around the speaker, the element velocity and the wave velocity are parallel. Therefore, we call the wave longitudinal. Remember that sound waves in general can propagate through any elastic medium. Any medium, basically any substance made of atoms or molecules that has elastic properties, so it can be stretched or compressed, can sustain sound waves. Air is our favorite example, but sound waves can also travel through water. Even steel, in this context, is considered an elastic medium. It would be very difficult for a person to stretch or compress a block of steel, but on a microscopic level, the iron and carbon atoms that constitute steel are elastic. They can be moved from their equilibrium positions, and therefore sound can travel through steel as well, glass also, pretty much any medium you can think of. What sound waves cannot propagate through is something like vacuum. Vacuum is not really a medium, at least in this context. There are no atoms or molecules there that could be displaced. So we need to have a mathematical description of sound waves, but before presenting that mathematical description, we need to discuss the notation that we'll use a little bit. Note that in the case of sound waves, each atom or molecule of the medium oscillates relative to some equilibrium position that it normally occupies when there are no sound waves. We're going to use the letter x to denote the equilibrium position, but because each atom is oscillating, we'll need a second variable to denote its displacement, and we'll use the letter s to denote that displacement relative to the equilibrium position. To better understand that, imagine here is our x-axis. Suppose we focus in on 4 specific molecules of some region of air. When there is no sound, when there is absolute silence, we can imagine that each molecule is basically sitting at some position, which we'll call its equilibrium position. In this case, molecule 1 is at x equals 1, and then the next molecule is at x equals 3, and then x equals 5, and x equals 7. Once a sound wave is generated and passes through this region of air, each one of these molecules begins to oscillate left and right. Sound waves are longitudinal waves, so the oscillations will be along the length of the x-axis. So the molecule here is not going to be oscillating up and down as it would in a rope wave. Instead, it's going to be oscillating left and right. Similarly, the molecule that's normally at x equals 3 is going to be displaced, and it's going to oscillate between, let's say, 2.5 and 3.5. The amount of oscillation depends on the amplitude of the wave and other factors, but the point is that the molecule that was formerly here is not going to stay there. It's going to move relative to that position. To describe that relative motion, we need a second variable, and that second variable is going to be called s. Some people like to use the letter y. However, y often suggests that the displacement is perpendicular to the x-axis. That's not the case with sound waves, so we won't use y, we'll use the letter s. The letter s is what tells you what each one of these molecules is doing relative to its normal equilibrium position specified by the variable x. So with these two variables, we can now describe a sound wave using this function here. This function here should look very familiar to you. It's the same trigonometric sinusoidal function that we've been using to describe oscillations of a mass spring system or a rope wave, for example. This function is basically telling us what the displacement of each atom is. More precisely, if you want to talk about the atom that is normally located at coordinate x, at a particular time t, its displacement is given by this function here. S, naturally, is referred to as the displacement or the wave displacement. It's measured in meters in the SI units. S max is the amplitude of the wave. It's measured in meters as well. In previous lectures, we used the letter A to denote amplitude. In the context of sound waves, A is usually used for area, as you will soon see. So instead of A, we'll use the letter S max. This name should make sense. After all, the amplitude of the wave is the maximum displacement. Remember that the sine function never gets bigger than 1, so this number out front is the maximum value that the entire function could have, so we're going to denote the amplitude by S max in this context. The rest of the parameters should be familiar to you. K is the wave number measured in radians per meter. It's related to the wavelength, 2 pi over lambda. Omega is the angular frequency. It's related to the period, 2 pi over t, and of course phi is the phase constant, which is measured in radians. We've been describing sound waves in terms of a displacement from some equilibrium value, and on the previous slide the function that I gave you for sound waves described the displacement of individual atoms or molecules. However, from a practical point of view, it's a little difficult to observe or measure those displacements, simply because in practice, the displacements of air molecules from their equilibrium positions happens very quickly, and it's an extremely small number, much less than, for example, a millimeter or so. So people who routinely work with sound waves, like sound engineers, prefer not to use displacement to describe sound waves. Instead, they prefer to talk about pressure. To better understand that, note that the motion of atoms creates variations in number density. So number density is the number of molecules or atoms that are normally in a particular region of space. For example, take the air in your room. In absolute silence, when there are no sound waves, the air in your room more or less has a uniform number density. So the number of molecules that are in one corner of the room are about the same as any other corner of the room. However, once you generate a sound wave, as these sound waves propagate through the air, the number density varies. So as the molecules begin to oscillate, you'll have regions where the number density goes up, so you'll have a lot of molecules bunched together, and you'll have regions where the number density goes down as the molecules separate from each other. These variations in the number density cause variations in pressure. So regions where a bunch of molecules are gathering together are going to be regions where the pressure goes up, and when the molecules separate from each other, creating a pseudo-vacuum region, are regions where the pressure goes down. If you've ever come across the ideal gas law, then you can understand this. According to the ideal gas law, pressure times volume is equal to the number of moles of a gas times the gas constant times the temperature. Using this equation, you can see that as N increases, then P increases, and as N decreases, then P decreases. If you've never seen the ideal gas law in a chemistry class, don't worry. In later lectures on thermodynamics, we'll spend a lot of time discussing this equation. For now, what's essential is that changes or variations in number density cause variations in pressure. Consequently, we can think of sound waves as pressure waves. We can think of sound waves as sinusoidal variations in not necessarily displacement, but in pressure relative to some equilibrium value, relative to some normal pressure. That equilibrium or normal pressure is usually 1 atmosphere. This animation demonstrates that. Once again, we have a cylinder and we have sound waves that are confined to the length of this cylinder. If you focus on the motion of the molecules in here, you will see that some of them have very large displacements and some of them have very small displacements. The graph here in black directly below the cylinder tells us what the displacement of each molecule is. For example, this red molecule here doesn't have much of a displacement for this particular wave. And so when you look at its graph, you can see that its graph is basically at 0 the entire time. Its displacement is nearly 0 the entire time. This other red molecule to the right is moving quite a bit. It's moving to the left and to the right by a relatively large distance. So when you look at its graph over here, the graph is oscillating between a maximum value and a minimum value, right? Indicating large displacements. Now, these displacements also correspond to variations in pressure. A region where the atoms are not moving that much is a region where atoms can bunch in together and then separate apart from each other. So that region corresponds to a place where the pressure can oscillate greatly. So this bottom graph in red is basically representing the same wave. However, rather than describing the displacement, it's describing the pressure. You can see places where the displacement is very small are places where the pressure can vary quite a bit. And places where the displacement varies quite a bit are places where the pressure does not vary much. I should mention that the horizontal line passing through this pressure graph does not correspond to a pressure of 0. It corresponds to some normal pressure or some equilibrium pressure. Usually that pressure is 1 atmosphere. So the pressure is oscillating slightly above or slightly below that normal pressure. So to make the discussion a little more precise, we can now say that there are 2 ways of representing the same sound wave. Imagine you have sound waves propagating through a cylinder of air or water or any elastic medium. Those sound waves can be described in terms of displacement or pressure. So we have the displacement representation of sound waves and we have the pressure representation of sound waves. From a practical point of view, pressure is easier to measure, and therefore a lot of sound engineers often prefer the pressure representation, but we need to be familiar with both representations. If you're using the displacement representation, then you're going to use the letter S to denote the displacement of a molecule that is normally located at coordinate X at a particular time, and this function here tells you exactly what that displacement is. If you want to use the pressure representation, then we'll talk about P for pressure, although it's common to talk about delta P. The reason is that the pressure is never actually 0. It's usually some change relative to ambient pressure or normal pressure or atmospheric pressure. So people often talk about delta P, and the amplitude for that wave is going to be delta P max. And otherwise, the function is essentially described by a normal trigonometric function like a sine function or a cosine function. Now notice a key difference between the displacement representation and the pressure representation. There is a phase difference of pi over 2 between the 2 representations. So you can use either representation, but you have to be careful about this pi over 2. The pi over 2 is basically telling you that points where the molecules have small displacements, so points where the molecules aren't moving that much, correspond to points of high pressure variations. Those are places where molecules can rush in 1 second, creating a high pressure, and then rush out the next second, creating a very low pressure. So if you made a graph of S versus X, for example, it might look like this graph for the same wave, if you graphed the pressure, you would notice that the pressure graph is shifted relative to the displacement graph by pi over 2. So if we take the top graph and shift it to the right by pi over 2 radians, then we get this bottom graph here. So both representations are acceptable. The displacement representation is theoretically more appealing, but the pressure representation is experimentally more appealing. Also notice that the pressure is never actually zero, so what we're plotting here on the bottom graph is really delta P and not P. We should discuss some of the other parameters of sound waves as well. Every sinusoidal wave has at least 5 parameters or 5 properties that are important. Whether you're talking about rope waves or sound waves, the sinusoidal waves will have some amplitude, which we used to denote using the letter A. Going forward, we're going to use something like S max, but there's always an amplitude. Every sinusoidal wave is going to have a wavelength, a wave speed, a period, and a frequency. There is, of course, the angular frequency as well, but that's related to the period or the frequency. And there is, of course, the wave number, but that's related to the wavelength. So for the time being, we just want to understand what these 5 parameters mean. A little more specifically, we want to understand how these physical properties are perceived by humans. More specifically, when you hear 2 different sounds, and they clearly sound different to you, how do we characterize that difference in terms of, let's say, the amplitude or the frequency of those 2 sound waves? This table summarizes some of the properties of these parameters that we've been discussing. It turns out what humans perceive as pitch really is a function of the wavelength or the frequency or the period of the sound waves. We'll make these relationships more precise later, but for now you should understand that when somebody says, oh, this is a very high-pitched sound, like somebody screaming, for example, what they're describing is the frequency. A high-pitched sound corresponds to a very high-frequency sound. Of course, a high-frequency sound then corresponds to a very low-period sound, because remember that frequency is simply the reciprocal of the period. So the period, the frequency, and the wavelength, which are all interrelated, describe the pitch of the sound. When you hear a sound that's very loud, you're hearing a sound that has a large amplitude. When you speak more quietly, when you lower the volume of your sound, then you are basically reducing the amplitude. So we'll make that relationship much more precise later as well. But for now, recognize that amplitude, roughly speaking, corresponds to the loudness or volume of the sound as heard by human ears. And these 3 interrelated parameters, lambda, frequency, and the period, correspond to the pitch of the sound. You might notice that what's missing from this table is the wave speed, and it turns out human beings cannot perceive wave speed. We simply do not have a sense for detecting how quickly sound waves travel through air. For later reference, I'll also mention that light waves have similar properties. For the time being, we want to focus on sound waves, but a little bit later in the course, we'll be talking about light waves. And light waves also have similar parameters. A light wave can also be described in terms of a frequency or an amplitude. In that case, the frequency of the light waves corresponds to the color that you perceive. So when you detect green light or blue light or red light, you're really seeing light waves with different frequencies. And when you see a really bright light, one that's almost bright, blindingly bright, you're basically detecting waves that have a very large amplitude, and low brightness, of course, corresponds to a small amplitude. So the same physical parameters describe all of these waves, but how human senses perceive these parameters can be a little bit different depending on whether you're talking about the human ear or the human eye. The wave speed for sound waves is going to be very important to us in many applications. It turns out human beings can't directly perceive the speed of sound, but if you're interested in how fast energy or a signal, for example, travels from point A to point B through sound waves, then you need to know the speed of sound. The speed of sound is given by this equation. In this equation, B is the bulk modulus of the medium through which the sound waves are traveling, and the Greek letter rho is the volume mass density of that medium. Here is the technical definition of bulk modulus, which might look familiar to you from your mechanics course. However, for us, this technical definition is not so important. What you need to simply understand is that the bulk modulus tells you roughly how stiff the medium is. So a medium that is very stiff, that is very difficult to compress or stretch, is going to have a large bulk modulus. That would be the case with, let's say, concrete or steel. But a medium that is very soft, that is easy to compress, like air, is going to have a very low bulk modulus. Of course, you should already be familiar with the volume mass density. It's the ratio of mass to the volume for that particular medium. We've also seen a formula for the speed of rope waves, and it might be interesting to compare those two equations. What you see here is for sound waves. For rope waves, the wave speed was given as tension divided by the length mass density. These two equations are obviously not the same equation, but note that they have a similar mathematical structure. So it turns out the speed of waves passing through any kind of a medium that has elastic properties is pretty much always described by a formula that has this type of a mathematical structure. The square root of some ratio that the details of that ratio is different for rope waves and sound waves. So you really do have two different formulas to memorize here, but the essential mathematical structure is the same. Here are some examples. For air at a temperature of 0 degrees Celsius, the speed is 331 meters per second. The speed is independent of the amplitude or the frequency of the sound waves. So you can speak more loudly and you can speak with a higher pitch, and that will not affect the speed of the sound waves. The sound waves will travel at this particular speed because this speed really depends on the properties of the air that you're using to communicate, not the frequency or the amplitude that you generate using your vocal cords. Underwater, the speed of sound waves is actually considerably faster. It's approximately 1,493 meters per second. So if you go underwater in a swimming pool, for example, and scream, the sound waves that you generate will travel much faster. You might be wondering why human beings can't communicate effectively underwater. That's simply because our ears are not trained to do that. So water tends to distort sound waves, as does air. However, our ears are used to the distortions introduced by air, but not accustomed to the distortions introduced by water. If you had lived underwater your whole life, then you could quite effectively communicate underwater. Whales, for example, are known to communicate underwater over very large distances. The speed of sound in rubber is approximately 1600. In iron, it's about 5,000 meters per second, and sound travels through diamond at an extremely high speed of 12,000 meters per second. Notice that in general, the more solid or more stiff the material is, the faster sound will travel through it. Now, this might at first seem strange. You might be thinking that the density of iron is much higher than the density of air. So rho for iron is much larger for rho for air, thereby reducing the speed. But you also have to look at the bulk modulus. The bulk modulus for iron is much, much greater than the bulk modulus for air. So B tends to dominate the ratio compared to rho. Consequently, the wave speed for iron is much higher than it is for air. Now, to be really precise, technically all of these speeds depend on the temperature of the medium. This fact is much more pronounced for gases than it is for solids. Technically, the speed of sound in diamond does depend on the temperature of the diamond, but the effect is not very noticeable. For air, the effect is quite noticeable, and therefore we need to know how this wave speed depends on temperature. That dependence is given by this formula here. We're not deriving this formula in this course, however, you need to know how to calculate the speed at different temperatures. According to this formula here, the speed of sound waves in air is equal to 331 times the square root of 1 plus the temperature divided by 273. The temperature must be provided in degrees Celsius, so the subscript C is reminding you that this temperature must be in Celsius, not Fahrenheit, and not Kelvin either. Notice if the temperature is 0 degrees Celsius, then everything inside the square root is going to be equal to 1, and we find that V is simply equal to 331, as indicated in this table here. However, as the temperature rises, then the speed of sound also rises, so generally sound travels faster through hot air than it does through cold air. Let's finish this lecture with a simple practice problem. The density of air at 30 degrees Celsius is 1.1644 kilograms per cubic meter. So this is the volume mass density of air at this particular temperature. Note that as air heats up, it expands, and therefore its density is going to change. In general, the density of air depends on temperature, so we're being very specific about the temperature in this problem. Calculate the bulk modulus of the air at this temperature based on this information. Now note that we have basically two formulas, or at least two formulas, for calculating the speed of sound waves. One formula is this one here, which tells us how the speed depends on temperature. The temperature must be specified in degrees Celsius. That's exactly what we have in this problem. So we can plug that in and find that the speed of sound waves in this particular air is approximately 348.7 meters per second. Now we have another formula for the speed of sound waves that tells us how the speed depends on the bulk modulus and the density. We can rearrange this formula and find that the bulk modulus is equal to rho v squared. We know what rho is, that's given to us in the problem. We know what v is, we just found it. We can substitute all of that in, and we find that the bulk modulus of air at this particular temperature is 141,592 newtons per square meter. I should also mention that there is a third formula for the speed of sound. It turns out this third formula is not useful for us in this particular problem, but I'd like to write it down anyways, just to remind you that you can always calculate the speed of sound waves using this formula, wavelength divided by the period. So if you know the wavelength and you know the period, this is a very nice formula to use, but in this particular problem, that information was not given. Notice that wave speed for sound waves is going to be quite important to us, so we have lots of different ways of calculating it. And that is the end of this lecture. Thank you for your attention.